Well, we meet again. This is the third and final survival analysis module, number 3, Deep Dive. I'm Mark Williamson for DaCCoTA at the University of North Dakota. So let's get our introduction underway here. Last time we wandered in the trees of survival analysis and examined how to determine survival times of a group or across groups. Today we'll swim over and examine the effects of factors on survival times via survival trees and regression models. We'll also look at detailed examples in R and SAS. But before we do that, let's review the basics. We know from the previous modules that survival analysis uses time-to-event data, and that the correct format is needed. At the fundamental level, you need a time variable and a status variable, either censored or an event, and the event is usually death. Because you cannot typically get a cohort, a group of subjects observed a long enough time to have all of them have the event, survival analysis almost always involves censoring, which you have to deal with appropriately. Now, in actual calculating things, common calculations are survival and hazard function, where the survival function tells the likelihood of still being alive after a certain amount of time, or whatever event other than survival. And the hazard function, both cumulative and just instantaneous, gives the hazard rate across time. Common visualizations include the Kaplan-Meier curves, which are non-parametric. But then parametric curves, we've learned, are also available, but you have to use more math. And if you want to compare two different curves, or of more groups than just two, you can compare it with the log rank test or other tests, but the log rank is most common. And if you typically want to extend beyond two groups or involve covariates, you need to use tree-based methods or Cox regression methods, both of which we will cover today. So coming back to our nice scope landscape visualization, we can see here that we have already accomplished our mission of dealing with survival times of a group and across groups in Module 2. So today we'll focus our attention on the effects of factors on survival time. We'll examine tree considerations and then regression considerations, as well as specific types of models for sort of unique data type. So for regression, the most commonly used model is Cox Proportional Hazards Regression, abbreviated to be Cox Regression. It's used to predict the probability of an event, death or otherwise, across time for given values of predictor variables. So this is an extension of basic survival analysis, where you might just be looking at sort of summary statistics of a group or comparing two groups against each other. Another way to think of this is analogous of going from simple to multiple regression, where you can have multiple factors rather than a single factor, like group. So here is a very typical sort of output. You would have your risk factor, maybe age and male sex. You have parameter estimates and a p-value. But actually, better yet than multiple regression, think of logistic regression and odds ratios. In logistic regression, you have a binary variable, and so you don't look so much at a parameter estimate, but as a odds ratio between them. You can kind of think of it the same way with Cox regression, because you can get this thing called a hazard ratio. You can see here what it tells us is, they say for a continuous variable like age, this was significant, which means as age increases, the hazard increases because this is greater than 1. Or for a categorical variable, like say current smoking, a discrete variable, we see that this is again significant, and what this says is smokers compared to the control, so non-smokers, have over twice the hazard ratio. Now, another way of explaining Cox regression is that it relates several risk factors to survival time by measuring the hazard rate. Again, that's why we almost always get the hazard ratio when we're doing Cox regression. Here's another way of showing the hazard ratio. This is data from the Framingham Heart Study, or Rx, so it's looking at survival rate. Rx is a therapy regime. This one is regression of a tumor. This is age, and then ECOG is patient's performance. We can see here there's a reference. These are all categorical, so compared to the reference, this therapy regime B looks like that is a significantly lower than the control, whereas looks like this is just barely significantly higher for those with regression, so a higher hazard. Age group slightly lower for the young compared to the old, and then for patient's performance there was no significant difference. So Cox models, the Cox model is semi-parametric, which means it's not non-parametric like the Kaplan-Meier curves, but it's not fully parametric. So it doesn't have quite the same set of assumptions. But as I said, parametric regression models are also available if you want a more sort of finely tuned or maybe more assumption-laden and difficult analysis. So let's turn to some more considerations. Again, we just said that Cox models are semi-parametric, and one of the things that means is they don't assume any particular baseline survival distribution. Now this is useful, and it's relatively easy to perform Cox regression, but it does have some limitations. One of the limitations is poor extrapolation. So if you want to predict survival, beyond the data, or kind of even like interpolation within data time periods, Cox regression isn't that great for it. Whereas something like a parametric survival model is much better at that. So it may be of great use to use parametric models, even though they're more complicated and take more assumptions. So parametric models, they model the data in more detail. They use a maximum likelihood approach with an appropriate distribution. So you have to supply a distribution and then make sure that distribution fits pretty well. Another way of saying it is they link survival time or hazard of an individual to covariates. So again, because this is the Cox regression style thing where there's multiple covariates, and it uses a specified probability distribution. So some very common distributions in survival analysis are the Weibull, exponential, log normal, though there are many more. In this big plot here, this is a generalized gamma. It's one of the most flexible models. You can see here it has a couple different parameters, sigma and q here. And you can see depending on the differences, you can fit a lot of different curves. You can have a linear curve here. You can have sort of this, not quite, almost exponentially decaying. You can have sort of flat. You can have almost U-shaped. So a lot of different things you can do with generalized gamma. And this is just one example to kind of show you. You can find the right model, or sorry, the right distribution to fit your model. And again, because different distributions fit different hazards data. So this is another great example where we have what's called the kernel density. It's just sort of the estimate of what the data tells us the distribution is, and this is fitting with a variety of different distributions. And what we can see here is that some do a very terrible job, like the exponential, of sort of fitting this density, while others, most notably things like the Gompertz here in green, do a reasonable job. Though you can see even with very flexible models, they sometimes still fit the data pretty poorly, which is why sometimes like the Kaplan-Meier, the non-parametric, or Cox regression, the semi-parametric work just fine or even better. And you can use parametric models for survival, hazard, and proportional hazards. Kind of all the sort of normal things you can do with other models. Okay, some more distributions here. Here's a good way to sort of remember what types of models, when it comes to parametric or not, and what's going on. So non-parametric models, Their baseline hazard has no distribution assumed, and their covariates have no distribution assumed. This is something like the Kaplan mirror. Semi-parametric models don't have a distribution for the baseline hazard, but some distribution assumed for the covariates. So this is like Cox regression. Whereas parametric models, they have distribution assumed for both baseline and covariates. So here is a great example of just another example of those parametric and non-parametric at the same time. Again, those step-like things, that's the Kaplan mirror with its confidence intervals, and then there's two different parametric distributions. One fits rather poorly, the blue, while the red one fits a little bit better. Though you can see here that neither fits particularly well, so sometimes even the best fit models that are parametric don't approximate the non-parametric Kaplan mirror very well, and you might want to just go with the Kaplan mirror because it's pretty robust. And here is some examples, again, of looking at these parametric models versus just the non-parametric. So this is exponential, these are just, and Weibull. These are output in R, and this is what graphs they produce, and comparing them to the Kaplan mirror. So for both of the exponential Weibull, with these chi-squared test here, it shows that gender is significantly different. So that's the, females and males. But the Weibull does a lot better fit close to those Kaplan mirror curves. So the Kaplan mirror are the yellow and the green, and the red and the blue are the parametric model. So some distributions are a lot better than others for specific data. And you have to really do a lot of work to fit these parametric models. And in fact, what you see here is, this is just Cox regression, and then the Kaplan mirror and the Cox regression itself actually, which is semi-parametric again, actually fits these even better than the Weibull. So we're going to turn this into an X and use our fancy green to say, actually, Cox regression worked best here. So again, even though you have more complicated models at your disposal, they're not always the best for your data. So that really stresses the need to try different models and check model fit, especially against visualizations. That really helps the eye understand what's going on beneath the surface. Now that we've gotten regression under our belt, let's turn to tree considerations. The more basic is survival tree analysis. It's an alternative method to Cox regression, which separates our events via partitioning rather than sort of a linear regression, or I guess in the case of parametric, nonlinear regression. So this is a typical looking tree. Each branch indicates a split via a value of the variable. So this, the most root tree part of it, it was split by grade, so like a tumor grade. And on this branch, it looks like G2. I think that's something to do with cell division. Age was over here, so on and so forth. And now ends, these are called terminal nodes, and they indicate the number of subjects with an event. So at this node, there's only one subject with the event, shown here. Whereas something like, say, over here, 8 of the 10 had an event. So you can kind of partition it out by that. Now, survival random forest, that is going to be the logical extension of survival tree analysis. So instead of building just one tree, which may only have sort of certain error or reliability, essentially it only does a decent job of detecting what the best tree is. You can make many trees and then average them. And then those prediction errors are estimated by resampling, also known as bootstrapping. So you can sort of get a feel for how reliable your outcome is. And then you can actually create survival and hazard curves from these tree outputs. And so we'll see some of that in our examples. That's all I think we really cover in trees. A lot of the survival trees are pretty analogous to other tree-based methods for other types of analysis, so I'm not going to tarry too long here. Instead, I'll go on a little more exotic considerations by trying to answer some specific questions that might come up with specific survival analysis data. So the first one here is, what if you have multiple events? So for example, you have multiple tumor sites on like mice, or sort of more abstractly, a very heterogeneous population that has a lot of variation that you want to control for. Well, you can use what's called frailty models. They account for correlation within a group by introducing a frailty term as a random effect. And so the idea is to consider events. So like if you have multiple tumor sites, each tumor as the locus as like the smallest level, and then the person the tumor's in, or the family, or the litter as the random effects. This also works for heterogeneous populations, because then you could say that the random effect is the location, like county or school or whatever that is. And so you can detect things with hazard rates by adding this frailty term. So this is example of unconditional hazard rate, and then different differential frailty terms that higher frailty terms have higher hazard rate, lower ones have lower rates. So that's kind of the general conception. And more broadly, it can account for the fact that individuals do not have the same underlying risk. So another consideration is, what if there are multiple ways to die? So for example, you could die from breast cancer, or you could die from stroke. So how to deal with this is called competing risks analysis. It partitions events that occur in models into discrete competing events. And the function that's most used in this is the cumulative index function. And so you can sort of split out things. For example, here we have death by melanoma and death by other causes. You can see the melanoma is the solid bars, and then other causes are the dotted. But then you can even split up between groups like non-ulcerated and ulcerated. So you can sort of partition out that stuff. Another question, what if time is discrete rather than continuous? We've been sort of treating time as days, years, months, or whatnot. Or if it's much more discrete, like for example, what do you have time until graduation, but it's only measured in semesters? You can't partition it anymore. Well, you can use essentially a form of logistic regression. Now, it is tricky to set up so that censoring is incorporated, but it can be done. So you can also see this reference 14 here. And there's a really great helpful introduction here. I'm not going to go too much into this in the examples, so check out 18 as your introduction. While continuing our other considerations exploration, we can ask the questions, what if you're interested in a covariate measure after follow-up? So most of our covariates are measured like before follow-up, like age, gender, ethnicity, treatment of drug. That's already set up before. But what if you have something like tumor response to treatment, which necessarily takes place after you're following up with them after a while? Well, there's a couple different ways to focus on this. One is landmark analysis. The other is time-dependent covariate analysis. In landmark analysis, you actually just select a fixed time after the baseline and then subset the population and just use Cox regression as normal for that subset. So in the example here is they set 90 days as the landmark after whatever covariate was, and then it's just as normal regression, looked at the different strata of delta A and 0 or 1. However, a little more complicated way to go about this is time-dependent. You have to set up data with multiple time intervals for each patient to account for different levels of covariate across time. So how you would reset this is you might have your subject, number 5, and instead of one time period, they have multiple time periods, so time 0, 90, 20, oh sorry, 0 to 90, 90 to 120, 120 to 185, and then the status, any of the covariates. Here's another example. Again, you have individuals here. This one just had there. And this one here. And you can see here is there's like typically set up as a start and stop date, 0 to 67, 67, 2081, and so forth. And you can get things like your status and other covariates. So again, that takes a lot of work to set up, but it can be done. Further question, what about survival estimates for those who have already survived a given time or event? This is known as conditional survival. You can have different converts for different conditions. For example, this is conditional survival given how for lung data given a certain amount of survival already. And so you can do things with that. And finally, what if you are an obligate Bayesian? You want to do Bayesian survival analysis. Well, guess what? There are Bayesian methods available too. So do not fret, do not worry. Bayesian methods. Well, maybe not in a hurry, but you can get them done. Okay, so we've gone through that portion of that. So please take the assessment found in the description below at this link. So let us be statisticians of action and not just talk. Let's look at some step-by-step examples. We will start in R with a prostate cancer data set looking at Cox regression with a single variable. So prerequisitely, we need to load a bunch of data sets, the most important one being survival again. And we'll look at the head, but we won't need to show that here just for time constraints. We'll look at the PG time, that's our time variable in years. It's relatively normally distributed table. These are our statuses. So 92 had no event and 54 had an event. Let's do a quick fit of the plot. And what we can see here is over the course of about 10 years, survival drops to about 50%, but then holds pretty steady there. All right, let's do our first model. We'll use this Cox pH, proportional hazards function. Again, we have the same sort of setup we had for our Kaplan-Meier curves or our log rank test. We have this serve function with both our time and our status variable. And then here now we have our single variable, which is going to be ploidy. And we'll get model summaries from this output here. This is kind of a tidy notation, so I like this here. And ploidy has 3 different groups. So it's a categorical variable. There's diploid, tetraploid, aneuploid. And compared, so this, because it's categorical, we're comparing tetra and aneuploid to our reference, which is diploid. That's why there's nothing here. And it looks like both tetraploid and then aneuploid, even more so, have higher hazard ratios, and that is significant. If we plot that, we can see the same sort of thing here. Best survival is the diploids, whereas the worst survival is aneuploids. And we aren't comparing between the two here, but I suspect that these wouldn't be significant, but this curve is significant compared to that other curve, and then this curve. Those are both significant. Okay, what if we want to use multiple variables? Well, we can do the same sort of thing. We're going to call this 2.1, Cox proportional hazards, same sort of setup, but then we have ploidy, and then all our other variables, age. We're going to have this EET. We're going to make sure it's a factor. So as grade, G2, and factor this Gleason. Don't worry too much about the variables. We'll just go with it. Here's a summary here, and we have quite a bit more. As we see here, it looks like, so ploidy, some of those are still significant. Age is not. I'm just going to kind of cross out things that aren't significant. Looks like this EET is not. So G2 is. Grade, that is significant. and it looks like Gleason is significant. So there we go. But then we can run another model and say we saw that grade and Gleason had quite a few categories, and they're sort of iterative. Higher numbers mean more, so maybe let's just try them as non-factors. It's more like continuous variables. We can get that sort of outcome here. And we can see here that there's a little bit difference. So now here, only tetraploid is significant. Age is still not significant. Our factor is not significant. Again, G2 is still significant, and then grade is significant, but Gleason is not. So it really depends on how you want to format these. I think what I really will want to do here is just keep ploidy and G2 and just sort of cut out grade and Gleason just to make things simpler here. And when we get this here, we see that, again, ploidy is still significant, but G2 on its own is not significant, so there might be more things going on here. So we could obviously keep messing around, keep trying to find model fit. I don't really think there's a model selection procedure for Cox regression the same way there is for more like multiple linear regression. So you'd have to kind of figure this out as you go and compare models. But the take-home point here is, just like with multilinear regression, multiple Cox regression takes a lot of finesse to build the right model with multiple variables. Alrighty, let's step up our game and try our hand at some parametric models. We'll use the same prostate cancer dataset. I'm using pretty much code for code from this reference number 4 here. So I'm not going to go into too much here, but essentially we need to set up hazard estimates, hazards, get this kernel density, get a bunch of different distributions, have them set up here, and create a parametric hazard using lists, then go through and get parametric hazards from all the distributions for this data set, bind it together, etc., set it up, and essentially once we get all that done here, again, I'll refer you to reference number 4 if you want to see this in action somewhere else. We're just going to plot it, and what this will give us is fit for our bunch of different parametric distributions against our kernel density in black here. And what we can see here for this hazard function, that nothing really fits that great. I mean, the best one maybe is going to be like the log normal or like the log logistic, maybe the generalized gamma, but you can see here, even with a lot of fitting with different distributions, you can have a hard time fitting distributions. Anyways, so because I'm going to say generalized gamma is as close as we're going to get, we'll use that distribution, do a summary here. And what we find here, I added just ploidy from our last exploration. And what we found is that both of those are significant. Again, and if we add in things like G2 and like factor grade, which was significant in one of the models, you can look here. Again, these are significant, G2 is significant, but factor grade as a factor was not significant. So here we go here. So really what we're doing here, in a nutshell, is we were trying to pick out the best distribution using all this previous stuff to make this nice plot here. But you could also go through and just run a bunch of these with different distributions and compare the models and see how they fit. That'd be another way to do it. Changing tack here. let's look at survival trees. So first, let's create this factor called progstat, just cleans up some of the language. We're going to have labels of either no, so like no event, or progression, because I think I was saying that this prostate cancer people were dying. It was actually whether or not you progressed, the event was progressing to the next stage. So an event was a progression. So we do that, we do tree one using this rpart function, and we're going to use all our variables with a method class, and just set up our viewing port, plot our tree, add some text here, and here we go. So at the top here, for this tree, the most important distinguishing was the grade of the tumor. If it was 1 or 2, equals 1 or 2, it went here, otherwise higher here. Or sorry, I think 1 or 2 meant it was over here. So then there was no progression in most of them. Higher grades, then the next point was this G2 value. If it was less than 13.2, you go over here, etc. And you can see there's different outcomes at all these terminal nodes. So, and see how on the rightmost ones, terminal nodes, it talked about the progression numbers, and then on the leftmost nodes, it was the non-progression, whether or not having events. So you can distinguish that. So this is another way of doing things with, I suppose, a regression. So let's up the ante and use survival random forest, which uses a bunch of trees. So we're going to use this RFSERC, same sort of setup here. We have all our variables, but now we can set the number of trees to be 100 and block size just 1. That's for the default. So now this makes 100 trees. We can't plot all 100, so let's just start with getting tree number 3 here. Get tree, and then say tree 33, and then tree 99. We can see this format is a little bit different, kind of a nicer. I kind of like this tree format. We can see that all the trees are different because each iteration will be slightly set up. See, for these two, G2 was the most important. Gleason was the most important here, which was different from our single tree where that was grade. And we can see different outcomes. And then so what you do with survival random forest is you take all the information for all these trees, and you can do stuff from there. Like for example, if we print just the sort of summary of our object, our trees we made. We saw we made 100 trees. We had a sample size of 134, deaths 49. For that, we mean prostate cancer progression. There's different statistics and stuff like this. What we really want to do is, first of all, plotting. So remember, our error rate, sort of how higher the error, the less robust, the less we can really trust our tree values. You see, initially, with only a few trees, it's pretty high, but then it drops down and keeps dropping. But we can see here, we could probably only needed to do about 50 trees to sort of get the average rate of error to drop down. But we did 100. We could certainly do more if we wanted to. So we're going to do applying these survivals. Let's just do a subset of 10. We can see these are all these different sort of Kaplan-Meier survival curves based on those trees, as well as cumulative hazard. You can see they can differ quite wildly. Some have pretty steep ones, some have shallower ones. And if we plot them all at once, it's sort of crazy, but it gives us this nice red line, sort of our mean, and that kind of, and gives us the cumulative sort of averaging of all those trees to what our survival curve looks like based on this tree-based methods. There's other stuff going on, but we're not going to really jump in there. But let's go back and look at our sort of raw Kaplan-Meier score. This was just survival without any covariates. We can see here that it's sort of broadly similar here, though this doesn't really take into account time after a certain amount of years. This is just sort of this initial curve here, and these have a pretty good concordance. So that was some survival random forest for you. Okay, we're going to shift to a different data set to look at a frailty model. I'll be leaning heavily on this reference 22 here. So lung cancer. We're not going to look at the head. That's fine. You can do it on your own. So let's look at if we have no random effects, so no frailty term involved, Cox proportional hazard reduction, time status, and we're just going to look at age. A summary here. It looks like, yeah, age is weakly significant, that as age goes up, the hazard goes up just a little tiny bit. So what if we add an institution effect? Because these lung cancers were from different institutions. So let's add a frailty term. In this model is plus frailty and then institution and then the degrees of freedom, which was 4 for this. And then we'll do a summary here. And we can see here that the frailty wasn't terribly significant, but it didn't change the hazard ratio or confidence intervals, which we weren't expected to do, but it did bump the p-value down a little bit, which suggests that maybe accounting for the institution effect did help partition out some of that error a little bit and give us a clear. Onwards, in case you SAS users were getting sad at being left out, we will remix our prostate cancer data set using Cox regression with a single variable in SAS. So now I'm not going to show you. I loaded in the data, and then I can run this proc univariate to sort of get a overview, including kernel density. Here's our RBPG time. Let's run. We're going to use proc life test to get our survival, our base survival plots, time and stat, and that's going to give us the exact same Kaplan-Meier curve we saw earlier. Then we can use proc life test to stratify this by ploidy, and we get those sort of outcomes here as well. And again, this isn't survival probability so much as, given the specific data set, what it is, it's overall non-progression probability, so keep that in mind, which means it's kind of like survival, where the lower the score means the less good outcome. Okay, so we're doing that here. And so if we want to do Cox regression specifically, we just had plotted those things earlier. We're going to use this pH, so proportional hazards reg, on our data, and we're going to use a ploidy as a class variable. Since it's categorical, we need to set that up, and we can actually set a reference variable, because otherwise I think it does it by alphabetical. We want to have diploid as our reference. And we have the same sort of model here, but now we have an equal sign for the ploidy. And what this gives us, so for example, we get these different fit statistics, which will be more important later, but it's good to know that you can see model fit. We'll kind of probably look at AIC for the other ones. And then our type 3 test, so this is whether or not ploidy is significantly different, and yes, it is. And because it's significantly different, we need to go and look at the outcomes. So again, here's ploidy, so there's aneuploid, and this is versus our reference, which is our diploid, and then also versus diploid. And we find that there were significant, and again, the hazard ratios, same sort of thing we saw with R. Aneuploid had over 4 times the hazard ratio, and tetraploid had almost 3 times the hazard ratio compared to the diploid. Okay, let's look at multiple variables. We're going to throw the gauntlet in and add EET and ploidy just as the class. Pretend the other ones are just numerical. Here's a fit statistics. And here are type 3 tests. So for each of these variables, whether or not it was significant, looks like, let's switch over to green here, friendly green. So this was significant, ploidy was significant, and G2 was significant. Okay, so let's try proc freg again, but then adding, kind of as we were playing around in R, let's add, because we know grade and Gleason are sort of more, or better, could possibly be categorical or numerical. Let's keep them categorical here. And here we have fit statistics, which is kind of interesting here. But now at this point, only ploidy is significant. So that depending on how you set up your variables, what you describe in them can be differently. You can see here that given this AICC has a slightly smaller than this, and so that this might be the better model, though you might want to sort of defend that in a different way. Anyways, we're going to jump over that here. Just keep it in mind, as with R, model fitting and multiple variables can get messy, and it's really up to you to define what the best model is, what variables actually matter, and defend your results. Anyways, I'm going to keep plodding along here. We're going to try this with just grade ploidy as classes and then G2 as our numerical or continuous variable. And then here is an AICC, or sorry, AIC, and all these are significant. So it's a little bit smaller model. And then I'm going to go in to look at the maximum likelihood, grade 1, 2, and 3. We can see here, I think it's all compared to grade 4. So this wasn't significant, but 2 and 3 were, so they had a lot lower hazards. And then ploidy was same sort of setup. These are higher than diploid, and then G2, since this is continuous variable, you just look at the parameter estimate, it's negative, so and the hazard ratio was lower. So essentially, as G2 goes up, the hazard ratio goes down, or so the hazard goes down. And again, keep in mind this plot that we made earlier. We can kind of compare the aneuploid and the tetraploid. And again, we can see that these are, clearly higher hazard than our diploid. Okay, we'll sidle along to some parametric models, leaning, as I always do, heavily on the shoulders of others. Let's reference 23 here with a nice blue. We're going to use proc life reg, class ploidy, and then everything's sort of the same except for you have a slash and then you add your own distribution. So we're going to try a log normal. We're also going to try another model with logistic, log logistic, and then gamma. And hey, let's do some exponential, and why not Weibull? So you see here with R, we did all that sort of coding to sort of run them all at once in one big kind of if-then function. This one I'm just being a little less elegant and just doing 1, 2, 3, 4, 5, 6 life reg steps and then comparing them. But hey, you got to do what you got to do. So here is the outcome. I am comparing AICC scores, so that's lower scores means better fit. And what we find here is that by far the Weibull has the lowest fit. So that is going to be the model we use from now on. We're going to use a Weibull distribution. So what does that mean? Well, we're going to use our Fuller model, which had ploidy, grade, and G2 with a Weibull distribution now, so it's parametric. Here is our outcomes. Looks like all of them are significant. Woohoo! Again, we're going to see sort of things here. Grade 1 is the reference here now, so it's a little bit different. Or sorry, not grade 1. Grade 4 is the reference. Again, this was not significant. These were significant. Looks like now here it's slightly set up where tetraploid is the reference, so that's why it matters to really be able to format your data. But the outcome is the same, it's just interpreted differently. G2 was again significant. And just to keep things in mind, this was our Cox regression, our semi-parametric table. And we can see right away that one of the downsides to the parametric models is they don't automatically have nice hazard ratios. You have to, I'm sure there's a function or a setting to set it up, but you have to dig into that if you want to do that. But broadly speaking of what's significant or not, the two methods are giving us the same answer, which is not surprising. All right, Bayesians. in the crowd there, your time has come. Let's do some Bayesian analysis on this prostate cancer data set. Okay, so what we're going to do here, first of all, we're going to reset our data just to make sure we don't have that problem where we had, I think, tetraploid as our reference. We don't want it as our reference. We want to have diploid. So we're going to create new variables that's called p-sort, so we can sort it properly so it's the data is in the right set so we can run it. So how this works, we'll do proc life reg, and this is just sort of the parametric model that we used earlier, but we're just using ploidy, Weibull distribution. We found that ploidy was significant, surprise, surprise. And now here, which is an important bit of why we sorted this, the reference is now diploid, which we wanted, and so it looks better and it's useful because diploid is sort of the normal state of cells, not tetraploid and aneuploid, so we can compare the two and they're significant and all that and so forth. Anyway, for the Bayesian portion of it now, same sort of setup here. So all of this is the same as what we just did with the parametric up until here, and then below here we're going to add some special Bayes everything seasoning sauce. Mixing my food metaphors here. Anyways, so there's a Bayes statement. You can set your seed, number of burn-ins, number of Monte Carlo simulations, etc., and our prior distribution information. This is very broad, sort of default. Anyways, when we run this, we get maximum likelihood, parameter estimates, posterior summaries, posterior intervals, and there's Bayesian analysis doesn't do p-values, so one way you can look to see if they're significant is these intervals, and since aneuploid and tetraploid compared to the diploid, these are negative and do not include 1, means, or include 0, which means they are significantly negative. So what it means is they have lower survival, or in this case, a disease reprogression or non-progression to the next stage. And just to compare these here, this is the non-Bayesian. Let's look at these estimates. You see that the estimates are the same between the two here. It doesn't change. So doing the same sort of thing, but how sort of confident we are and how we estimate things is different. Anyways, but the real fun meat of Bayesian is the nice plots we get. So we get our Monte Carlo chains. This looks pretty good. You can look at these chains and make sure they're sort of even, not too crazy for our fit statistics. And then we get our posterior distribution. We see that for poly and for the aneuploid, that is significantly lower than 0, it looks like, within the knife. And same with tetraploid. So those are significantly different from the diploid. 0 being being the reference value, setting diploid at 0. So I hope the hearts of all you Bayesians out there were appropriately swooned through the Bayesian analysis. But speaking of hearts, let's look at heart transplant data so we can take a loc at time-dependent variable analysis. We lean very heavily on this. I'll leave most of the details to that. Anyways, you're using proc freg with heart data, time and status, and our time-dependent variables are X status and ACC age. And we'll format something so that X status is either going to be 0 or 1, depending on time and wait time. We'll do model fit statistics and looking at our analysis of ML estimates. We can see here that X status is not significant, but I think this is accelerated age is significant. So as it increases, this is positive, so as accelerated age increases, so does the hazard ratio, just a little bit. So we can also do this as more variables, like for example, we can add X status, X age, and X score. So in this one, accelerated age was not actually time dependent. I made a misstep there. but we can have all of them X stage, so you set up things, so you have either them status, age, or score at 0, or have them at 1, or different things here. Anyways, leaving most of the details to this reference 24 here. Fit statistics again, actually a slightly lower AIC score, so this might be a better fit model. And then here we go here, and what we see here is status and age as time-dependent variables were significant, while score was not. And how, since this was negative, so as status went up, hazard ratio went down. As age went up, though this is positive, hazard ratio went up. So there you have it. And finally, let's look at a leukemia data set and look at some competing risks. So we'll use PROC-FREG. So we're using this BMT, bone marrow transplant. We're looking at the hazard of relapse. We'll set up our group variable as a class. We're going to order it, specifically model, so time and status. But now instead of just having 0 here or 1 here, we're having 2 different ones because we have competing risks. We're going to group as one of our predictor variables and then log wait time as well. And we will set up this hazard ratio and pairwise differences so we can see things. So then what this means is this is cause-specific hazard, so competing events are treated as censored events. So in this one, I think they could either die from, or either relapse, I think, or die. Oh, here we go. So censored, relapse, or die without relapse. So we're really looking at relapse, so that's 1. So then we treat both censored and dying without relapse as censored. Okay, and what do we get here? Well, what do we get here compared to the group is what we care for. This is AML, low, high risk, and all. It looks like compared to all, high risk is not significantly different, but the low risk is significantly different, and it has a lower hazard ratio than the all. And wait time was not a significant predictor. And we can look at cause-specific hazards for group. And then this is kind of nice because then we can look at all the comparisons. For example, the low risk versus high risk. And high risk versus low risk, that's just inverses. Let's look at the high versus low risk. High risk has a lot higher hazards than the low risk. And conversely, low risk has a lot lower hazards than the high risk. And we already looked at kind of these in these other ones here. Anyways, though and so forth. So this hazard ratio with cause specific is nice because you can look at all the comparisons rather than just comparisons each to the reference. But what does this mean here? So let's create this data called risk. We'll do PROC-FREG, and we'll have this baseline term now, and we'll have specific plots. What this gives us here is, again, this subdistribution risk. So this is, again, those comparisons and maximum likelihood for just those who had relapse. You can look at the computed risk usually uses cumulative incidence functions. You can see here that the high risk had a lot higher cumulative incidence function than the other two, though all was sort of in the middle, and then low risk had much lower. Anyways, sort of skipped over a lot of stuff, but that's sort of what you sort of do in a nutshell. All right, with that, assessment 2 is here and in the description below. So some caveats and concerns. Some of this stuff I sort of breezed over or sort of jumped through, so obviously this is not the end-all be-all talk about survival analysis. So to put that in another way, we just scratched the surface on many of the examples. There are lots of tweaks to exploration, model parameters, and graphing. For example, the Cox multiple regression, we looked at different models and we sort of played around, but there could be a lot more you could do with that. We didn't cover some specific types of analysis. We didn't really have time. We didn't do landmark analysis, conditional survival, logistics style regression, but those are things we talked about in the sort of the survey topics. But those can be done in both R and presumably SAS. And again, model fitting and interpretation are important to get right. With these Cox regressions, parametric models, things get a lot more complicated. You might be running multiple different models and comparing to each other, so you may need to make sure you fit them right and interpret them right. And different procedures will have different outputs. We saw that for parametric models in, say, SAS, they didn't give hazard ratios natively, whereas the semi-parametric did. And again, the same sort of attention you need for multiple regression or generalized linear models applies to things like parametric models or multiple Cox regression. And we saw that even with these flexible parametric models and doing all this fancy math stuff, even a flexible distribution may be a poor fit. You might just want to do Kaplan-Meier or Cox regression, something simpler and less parametric. And in fact, though, if you want to get even more mathy and off in the wonderful woods, you can look at things like splines or fractional polynomials as needed, as sort of, if you go to these references here. And as always, start simple and build from there. Start with a simple model that you understand and build up, add terms, etc. So don't just take my word for the fact that you can use survival analysis for things. Let's look at what other papers in the real world have done. So this is a paper in 2014 on biomarker profiling with nuclear magnetic resonance spectroscopy for all-cause mortality, an observational study of a lot of people. So looked at identification of ambulatory persons at high short-term risk for death with targeted prevention, looking at biomarkers for mortality through blood specimens in cohorts. And here's some examples of cumulative probability of death based on different quantile risks. Here's again another cumulative probability, so we see that sort of competing risk sort of thing. And here are hazard ratios for a bunch of these different variables. So this is a very typical output of these tables, hazard ratios, p-values, looking at prediction model with and without biomarkers. So there we go. There's some survival analysis going on there, quite hard. Looking at a different paper, different outcomes between breast conserving surgery, breast radiotherapy, and mastectomy in metaplastic breast cancer population-based study. So it turns out these type of breast cancers are rare, so you want to look at survival outcomes. So this is a landmark analysis looking at a lead time. So what they did was it looked like they looked at follow-up time. These are the different surgical or radio procedures, and looked at the survival between the two. And this one is breast cancer. So this is overall survival, breast cancer specific survival. And this is I forget what they call it, a forest plot. But essentially they looked at all the different variables and whether they're significant with hazard ratios. And again, landmark analysis picks a time. So it looks like they looked at 6 months, and then just you do normal Cox regression. All right, another one we'll look at, get outside the strictly biomedical and look at pine trees, 3 hierarchical levels, looking at induced stress. So they did these stress experiments and carbon garnet experiments on survival and growth of these different pine trees. So looking at a survival probability, they use a Kaplan-Meier method, conditional probable. So this is conditional sort of survival. These are these different plantings or different these different ones. They're different like clones or locations. You can see differential survival based on that. Okay, so let's summarize and conclude this already overbearing survival analysis talk. Survival regression is the survival analysis equivalent to linear regression. Surprise, surprise. Now, parametric models are the survival analysis equivalent to generalized linear models. And tree-based methods are an alternative to Cox regression, and there are a variety of particular methods, frailty models, competing risks, time-dependent variables, so on and so forth, etc., often to the distance of survival analysis, that are used under specific circumstances, trying to answer specific questions like we posed. So at the end of the day, though, we can determine the effects of factors on survival times using one or more of these techniques. With that, I will give you not one, oh no, but 2 pages of references for you to dig into and confirm that I am not just making these things up. And in fact, there are people who know these things far better than I do that you can lean on. Especially, I'm going to have a huge shout out to reference number 19 here. Great tutorial about survival analysis in R. Finally, at long last, we've come to the end. Acknowledgments. As always, I am supported in the DaCCoTA grant under an NIH Health Award, so please cite the Biostats core if you find this useful. Have a great day and try to be one of those censored data in a survival curve. Thank you.